Okay, this is a warning before you watch this ridiculously long video. First of all, this video is getting too long, so I stopped at after doing question number 10. I'm going to make another video that does the last 10 questions. Okay, the warning is this. Your goal is to understand. These are practice problems. Now, if I do these problems for you without you trying them for yourself first, then it's not going to be a benefit for you because you just got help for the problem. You don't know if you really understand it. You only know if you really understand a problem if you can do the problem by yourself with no help. So, you can either try to find another problem that's just like the problem that you got help on to see if you understand it, or you can come back to the problem that you got help on the next day and try to do it with no help. But even still, that's not the best way to know for sure if you understand that problem. But coming back to it later is still very beneficial. One reason why the video might be longer than it needs to be is because I try to go through a problem and think through it the way you might be thinking through it, because I think that might really help your understanding. But another way around that is you can just speed up the playback speed of the video by clicking on the settings in the YouTube window, viewing window, and just speeding it up to like 1.25 or 1.5 or even 2. It's kind of funny sometimes because my voice sounds funny. But that's how you can speed it up. So, if you have any questions, please leave me a comment. You can ask for clarification or have a question. Somebody else might even answer your question. I will try to get to your question as soon as possible because I get an email every time you guys comment. Alright, hope it helps. This is the AP review for Chapter 5. Alright, whenever I get problems like this where they give me an area of an interval right there, there's the area, here's another area of a different interval, but same function. And then they give you this interval right here. To find this, I like to draw lines. Let's draw a line. Let's go from 0 to 3. From 0 to 3, we know that our area is 6. So I'm going to put a 6 right here. And then this one right here goes from 0 to 2. So 0 to 2, 2 is like right there. So from here to here, we have an area of 4. So the whole thing is 6, and that part is 4. This right here says what is the area from 3 to 2. It does not say from 2 to 3. I think just by looking at this, you can see that the area between 2 and 3 is 2, because 4 plus 2 would equal 6. But if we're going from 3 to 2, that means we're going backwards. We have to flip or change the sign of 2. So that means our answer is going to be -2. Alright, let's do number 2. I'm still not sure why it says C right here, because you don't need a calculator to do this one. Maybe it's a conceptually based type problem. Alright, from 1 to 4, our area is 7. Our area underneath the f of x curve is 7. So now we're supposed to find this. This actually wouldn't be that bad if you split it up. So we're going to split this up. This is known as the linearity of integrals. Let's see, we're going to go, and I'm going to have the f of x right here, and I'm going to take out the 2 and put it in front because it is a scalar. The 2 is a scalar. dx, and notice I didn't put the plus 5. And so over here I'm going to have from 1 to 4, and then this is going to be the 5. We can do that. We can find the area underneath the curve of 5, because that's not really a curve, it's just it's a constant function. It's a line, horizontal line. I don't have to put the 2 in front of the 5 one because the 2 is only multiplying to the f. It's not multiplying to the 5 as well. So for this first one, we know what this equals because the problem tells us it equals 7. So 2 times 7 is 14 plus whatever we get right here. Now that one, think of it like this. Here is the line at 5. From 1 to 4, we're trying to find the area underneath this. And so we just have a rectangle. So the distance between the 1 and 4 is 3, and our height is 5, so 3 times 5 is 15. You just add these guys together, you get 29. Now if, I explained it with the line and the image and everything because I think it's easier to understand, but really what you need to do when you get a constant inside of an integral, just subtract the upper integral from the lower integral, lower integral from the upper integral, so 4 minus 1, and then multiply it times the constant. That's how you get the 15.
So our answer is 29. That's the letter D. Alright, so here we go. This is a derivative function, and normally we put the derivative function inside of an integral. It's funny. This one is a calculator one. So we got the 1 plus x to the third power inside of that. Actually, never mind. You don't need a calculator. Let's see. This is going to be from 1 to 3. Now, if I take the antiderivative of this, this is f prime. If I take the antiderivative, I get f. But since I have an equation right here, I can definitely do the antiderivative, the integral of this. Oops, I forgot to write dx. All right, so this is whatchamacallit, u-sub problem. All right, so I'm going to try u-sub. Let's do it. I'm going to say u equals. Oh, where'd you go, u? Okay, u equals 1 plus x to the third power. Derivative of both sides is du, and this side you're going to get 3x to the second power dx. Well, dx is technically under here. We moved to the other side, but that doesn't matter. Now, this is a problem because we still have an x with the dx, and there's no x's outside of this. So if we tried to plug this in, it wouldn't work. So we got to come up with something different. Now, because it does say C, and because I'm looking at my answers right here, I'm assuming that we're going to be using a calculator. So let's hypothetically take the antiderivative. If I hypothetically take the antiderivative, I would get capital F, because this is f prime. If this is f prime, then our antiderivative would be capital F. And then we would put an x right here, and then we would plug in the 1 and the 3. Then you would get f of 3 minus f of 1. Then notice that f of 1 equals 5. We don't know what f of 3 is, and actually that's what we're looking for. So this right here equals this. So let's rewrite that. So we have 1 to 3 square root of 1 plus x to the third power dx equals 5, or f to the third, or f of 3 minus 5. So in order to find this, what we're going to have to do is we're going to get this f of 3 alone by adding 5 to both sides. I'm going to add 5 over here, and to find this answer, we're going to have to use a calculator. Put this in the fn function. So press math, and then you're going to press I think it's number 9. There's your buttons. Math, and then FNINT. This is number 9 on most calculators. Then you're going to put in all this, press enter, and then add 5. Now, this will look exactly like that if you have math print as a mode. Newer calculators automatically have that. If you have an older TI-84 Plus, then you might not have it. You can update your calculator, but if you don't have the right cord, you can't do it. So the way you would plug this into your old calculator would look like this. FNINT, and then you'll have an open parenthesis. You'll put the function in, then you'll put the x in, that's for dx, and then you'll put the lower bound and then the upper bound. Press enter, and you should get 6.229953, keeps going on. Okay, don't delete that number, just take that and then add 5 to it, and then you'll get 11.230. Let's attack number 4 here. Number 4 says find f prime of 2. So that means we're going to take f, take the derivative of it, and then plug in 2. The beautiful part is that f is written in integral form. And because of the fundamental theorem of calculus part 2, we know that this number doesn't matter. That 2 is just a constant. This x is going to look like it's just getting, it's going to replace the t. So we have x to the third power minus 1, the square root of that. This equals f prime of x. So I'm going to plug 2 into that. So I'm going to go 2 raised to the third power minus 1. So it's going to be 8 minus 1. So you have the square root of 7. There's your answer. All right, weird problem. We got this crazy integral right here. What's weird is there's no variable right here. Don't be fooled by that pi. That's a constant. This one does have a variable. So how would we take the derivative of this so we can find f prime? Let's do it to it. I'll show you. Calm down. Negative. And I'm going to put that 3x up here and the square root of pi down here. See, this pi, the square root of pi is insignificant. He makes the constant. If you've learned anything about area of functions, you know that that's a constant, dt. So, fundamental FTC 2, whatever, part 2. It says that I'm just going to take this and plug it in. So, it's going to say cosine of 3x squared. And that's inside of the cosine. Don't forget the negative. Oh, and don't forget this. Is this a function? Yes, it is. It's a function inside of a function, which means we would be using the chain rule, so then we have to multiply this by 3, because the derivative of 3x is 3. So that's actually a negative 3 out in front. So let's see what we got here. Oh, looks like they squared it. So let's do negative 3. We're going to clean up our act here. And we have 3x squared, which would be 9x squared. That's going to be inside of our cosine, so that's going to be letter E. E. No, that says sine. Dang it. Cosine. That one. C. If I just lost you, check this out. FTC 2 pretty much says you could take this and plug it in when you do the derivative of this whole thing. It's like the integral goes away. Let me show you why. If you do the antiderivative of this, actually never mind, can't do antiderivative of this because even if I try u-sub won't work. Anyways, just check out one of my other videos on a fundamental theorem of calculus part 2. The thing about this is there's a function inside of the f function, the capital F function. So because there's a function inside of a function, that's why I have this times 3. Now, let me think of another example. Okay, I just wrote another one. Here's the g function. It's written in integral form. And so you have this x right here, and you have this t is different than the x. Okay, so what you would do in order to solve this is you would take the antiderivative of this, and then you would plug in the x and the 3 and subtract them. If I take the antiderivative of this, actually let's make this not a 5, let's make that a 4, because it'll kind of clean it up. Right, let's take the antiderivative of this. We would add 1 to the 4 to make 5, then we would divide the 10 by 5, and then we would put a t with this 3, and then we would plug in the x and the 3. So when I plug in the x, I'm going to get 10x to the 5th. Nope, I'm sorry. Let's simplify. 10 divided by 5 is 2, so we get 2x to the 5th power minus 3x. And then we have this 3. So I plug in the 3. I'm supposed to subtract whatever I get when I plug in the 3. So I get 3 raised to the 5th power minus 3 times 3. Now I'm not going to simplify this, but I do know that I'm going to get a number with that. This is now g. I wrote the area function, the integral, in a different form, which is fine. It's totally legal. We just used the fundamental theorem of calculus part 1 to take the antiderivative and plug in these things and subtract them. Now what would you do to take the derivative of this g, what we got? So if I took the derivative of this, we would go, first we would drop the 5, multiply it times 2, so we would get 10. Then we'd have x to the 4 because we would take 1 away from the 5. And then we would get minus 3. This x would go away. And then there's this guy, which we got from the 3. Remember? Now that's just going to be a constant. It's going to be a number. So he is almost insignificant now because the derivative of a constant is 0. So here is g prime. Now look at what I could have done. Instead of doing all this work to get to here, I could have went back up here, ignored this 3 because I know it's going to give me my constant, and just plug this x into that t. Would have gotten the same thing. That's FTC 2. Okay, so this is a table for capital F and F prime. we're going to use the following table to compute the left-hand Riemann sum. Now, the integral stands for the area underneath the curve that's inside of it. Okay? Okay. So, all these points in the first row are the ones we're going to need in order to find the area inside of this integral. Area underneath this function inside of this integral. So let's draw x and y axis to get an idea of what's going on here. We're going from 1 to 3. And in between 1 and 3 we have these numbers. So we have 1, 2, 3 numbers. This is 1.75. That's silly. I said 1 and I wrote 3. And then we have 2, and this is 2.5. Okay, so what are all these numbers here for? I'm going to use a left-hand Riemann sum, 4 subintervals. Okay, there we go. We got 4 rectangles. Now, I'm going to draw all the rectangles kind of just like so. I don't know if this is the height of each of them, but we got 4 rectangles here. And our job is to find the height of each of those so that we can then find the area of each of them. Now on the left side, remember this is the graph of f. On the left side, so let's look at this rectangle. The left side is this side. So whatever the height is right here at 1, whatever this point is, so that point is 1, 4. The height is 4. So this rectangle's area can be found by going 4 times the base. So whatever the base length is, you just multiply that times the 4. So we're going to go 0.175 is the distance there. And then for the next one, for the left side of our next rectangle, that point is 1.75 and the height is 12. So this would be 12 right here, and 0.25 would be the width between 1.75 and 2. And then the next one would be, see the height of 2, at 2 we would be at 6, so 2 comma 6. So the height is 6 times whatever this is, that looks like it's 0.5. And then the last one, the last point would be 2.5 and then 12. So that's our height, the 12 is height, and the last base right there is 0.5. So we know how to find the area of a rectangle. We just take one side and multiply it times the other side, base times height. So that's what I'm going to do for each of these. So we're going to go 4 times 0.75 plus 2.5 times the height of that one, which was 12. And the third rectangle, we have a height of 6, then we multiply that times 0.5. And the last one, we have a height of 12, we multiply that times 0.5 again. Now there is a way of doing this with tables, with the stat edit button that we worked on in class, but if you just wanted to plug this into your calculator really quick to see what you get, this would also work. Actually, I thought it was just easier just to plug it in, so I got 15 right there. That's your answer for that one. So for this problem, we're going to be using the table again. So I have our table sitting right here. We have f prime inside of our integral, and we're trying to compute it. So at first glance, it doesn't look like we would be able to do this, but if you know the fundamental theorem of calculus, you know that we can take the antiderivative of f prime, which equals capital F. So we have capital F, which is the antiderivative of f prime. Then we're going to plug in 3 and 1 to that. This would equal capital F of 3, and then we would subtract capital F of 1, and we could get these answers from up here. Here's capital F of 1, and here's capital F of 3. So now we just have to subtract those. So we get 4 minus 2. Whoops, I'm sorry. It's 2 minus 4, which equals negative 2. And that's your answer for number 7. In this problem, it's helpful to remember our big overarching idea in calculus, and that's if you have a function, you take the derivative of that function. The
derivative function is a rate. The function that you started with is the amount. Amount can be a lot of things like distance, or in this case, amount of water, how much water. So what we need here is an f function. We were not given an f function. This is called a rate function. It says gallons per minute. So what we can do is set up an integral, or take that, because an integral takes the antiderivative of the rate function, and that would give us an amount function. Okay, so if I put in the interval, the actual interval, this would give me the amount of water between 0 and 2 minutes. We're given the amount of water at 2 minutes. We're not given the amount of water at 1 minute. Now, if you know FTC, the fundamental theorem of calculus, you're already thinking that this is going to equal the antiderivative of this, so then we would get t to the third, then you have 6 in front divided by 3, so this is just going to be a 2 in front, plus a t, and then you're going to plug in 0 and 2. After plugging in the 2, this 2 right here, plugging that in the t, we would get this, then we would subtract what we get when we plug in 0, but this is unnecessary because when we plug in 0, we're just going to get 0. This is all going to be 0 when we're done. We get, 2 to the third power is 8, times 2 is 16, plus the 2 we get 18, which is really weird because this problem tells me I'm supposed to have 32 gallons. So what does that mean? This means that when we're at 0, we're not starting off with 0 gallons. We're at 0 seconds in our minutes. We're not starting with 0 gallons. We're starting with 18 plus something. I'm sorry, we're starting with something that adds to 18 to give us 32. So if f of 2 equals 32, then what are we adding to 18 to get 32? Because we just found out that from 0 to 2 minutes, we are adding 18 gallons. Like the water is is the amount of water gained during that time is 18 gallons. So I mean, it's pretty simple when you think about it like that. So what plus what? I mean, you just subtract 18 from this side, and you get, let's see, you'll do that thing. You get 4, so you get 14. Our question mark equals 14, or our variable. Okay, so we started out with 14 gallons, and then added 18 so that we would have 32. So how are we going to figure out how many gallons we have at 1? Well, we're going to do the same thing, but instead of putting a 2 there, we're going to put a 1 there. Because we want to find out how many gallons of water we are gaining from 0 to 1 minute. And since now we know what we start with 14, we're just going to add 14 to that amount. So let's put 6t to the second power plus 1 dx. Alright, I'm going to have to clean up this screen here. So I do my antiderivative thing again. I know that I get 2t to the third power plus t. I'm going to plug in 0 or 1, then 0, subtract those. And after I do that, I'm going to have to add 14 to that. So I get, see, if I plug 1 into this, it's just going to be 1 times 2, so we have 2 plus 1. And then we're subtracting 2, we plug 0 into it, but this is pointless because we just get 0. And I'm going to have to add 14 to that. So 14 plus whatever we get. And this is 3, so we get 14 plus 3, which equals 17. So, just to recap. We are told that in this tank, at 2 minutes, we have 32 gallons. In this tank, at 2 minutes, we have 32 gallons. The integral that we set up from 0 to 2 just tells us how much water we gain within 2 minutes. That does not tell us the amount of water that is currently in the tank. It just tells us how many gallons we gain. And we found out that we gained 14 gallons during, I'm sorry, we didn't gain 14 gallons. We found out that we gained 18 gallons during that time from 0 to 2. And then what we did is we found out how many gallons we would have to add to 18 to get to 32, since we knew at 2 minutes we had 32 gallons in the tank. And so we learned that 14 gallons were in the tank before we started our time at 0 minutes. And so we do this integral again, but this time we go from 0 to 1. This integral tells us how much water is gained in the tank from 0 to 1 minute. Remember, this is the rate. This is the rate at which the water is flowing into the tank. We can do this right here from 0 to 1, the integral of the rate, to find out the amount that is gained from 0 to 1 minute, which we do. We found out it's 3, and so we just had to add 3 to the amount of water that is currently in the tank. And we couldn't find the amount of water that was currently in the tank unless we knew that at 2 minutes we had 32 gallons in the tank. Okay, this problem looks like it's a u-sub problem. So I'm going to make u equal x squared because, and I chose x squared because x squared is inside another function. It's the most inner function. Most of the time that works. So I get the derivative of u with respect to x is du over dx, and then this side we get 2x. We're going to move that dx to the other side and then start replacing things. First, let's replace the x squared. So we got 6x sine, and then we're going to put u in for x squared dx. Now our next job is to get rid of that dx, and so I'm looking over here and I see I have a 2x dx, but over here I have a 6x dx. We could rewrite this like this. Now normally what I would do is I would rewrite this one over here to make it look like 6x dx. So let's do that. If I multiply both sides here, which I'm allowed to do, whatever I do to one side, if I do it to the other side, the equation still stands true. We get 3 du equals 6x dx, which is what we wanted. We wanted 6x dx. So I'm going to take out 6x dx, and in its place, I'm going to put 3 du. Now 3 is a scalar, it doesn't have a variable attached to it, so I'm going to put them out in front. So we have 3 integral sine u du. Now I just have to take the antiderivative of sine, which is negative cosine u. We have to multiply this by 3. Put a 3 right there. And then we have a plus c. Let's sub the u back in, so then we have negative cosine x squared plus c. And so our answer is letter C. Alright, last one for this video. This video is already too long. Alright, now this one threw me for a loop for a second. We have to do some extra fancy things. So let's get started. The most inside function looks like it's x minus 1. When I take the derivative of both sides with respect to x, I get du over dx on the left side, and on the right side I get 1. Let's move the dx over to the other side. So now let's substitute in what we have. The first thing that we have, man, my integrals, oh, that's better. Okay, 4x, we put a u in for the x minus 1, and then we have a dx right here. We don't want that dx there, we want a du. It looks like du goes in for 1 dx, and so we have our 1 dx there, and so when we sub it in, we get something like this. The integral of 4x u times du. Now we have a problem. We have an x in there with a u. That x cannot be there. Alright, so this is where we have to get a little fancy. What we're going to do is we're going to look at this right here and make x equal u to see what we could sub in for the x. So all we got to do is add 1 to both sides. So we're going to add 1 here and add 1 here. So we get u plus 1 equals x. Oh wait, let's plug that in and see what it looks like. Oh, this 4 is a scalar, so we can move him out. So let's go ahead and move him out. And for this x, I'm going to plug in u plus 1. And then we have u raised to the 1/2 power. I'm writing the 1/2 power instead of the square root because I saw, as I was writing, I was thinking, oh, I can distribute this u to the 1/2 power. Actually, I don't need to have those parentheses. We can just say u to the 1/2 power. I can distribute that u to the 1/2 power to these guys. And then it looks like I can easily do the antiderivative of that. So we got u to the 3 over 2. And now let me show you how I got that. This is a u to the 1 power, and I can write the 1 as 2 over 2. If I multiply this u to this u, I add the exponents. I chose 2 over 2 because this one has a denominator of 2. So now I just have to go 2 plus 1, which gives me 3. That's how I got 3 over 2. And then we have 1 times u to the 1/2 power. Now this problem doesn't look that bad. We can very simply do the antiderivative of each of those. We just have some fractions to work with. Alright, so antiderivative of this first one. The first thing we're going to do is we're going to add 1 to the exponent. But instead of writing 1, let's write 2 over 2. So we get u raised to the 5 over 2. And then we're going to divide that by 5 over 2. Or, if you're quick enough, you can just multiply by the reciprocal instead of dividing. Now reciprocal of 5 over 2 is going to be 2 over 5. The next one, we have to add 1 to the 1/2, and so that would be plus 2 over 2. So we get u raised to the 3 over 2, and then we're going to multiply by the reciprocal again instead of dividing by the fraction. Alright, we got a plus c here, but let's not forget we have to multiply all this by a 4. Now what some like to do, I've seen this done before, is they multiply everything by 4. And when you multiply the 4 times the c, it just changes the c into a different constant. So instead of using c, they use d. But I'm not going to do that. I'm just going to multiply this by 4. So we have 8 over 5, u to the 5 over 2, plus 8 over 3, u to the 3 over 2, plus c. Now you might be getting excited because you might be able to see which answer we're going to get when we're finished. I'm going to put the u in, and then I'll change the fraction exponents to square root signs, radicals. So we have 8 over 5, and we're going to plug the u back in, which is x minus 1. I got that from this. And that's being raised to the 5 over 2. And then we have an 8 over 3, x minus 1, and that's being raised to the 3 over 2, plus c. Alright, so these 2's, the denominators of these fractions, those are radicals, those are square roots. And so we're going to rewrite that with square roots. So we have 8 over 5, square root of x minus 1. Now that power, the 5, that's a power. That power can go on the inside with the x minus 1, or it can go on the outside. It doesn't matter. It goes on either. And then we have plus 8 over 3 square root of 8, or x minus 1, and this one is being raised to the 3rd power, plus c. Alright, this answer is complete. Which one of these answers looks like that? It looks like, yeah, this one right here.